Hey guys, what's up? This is your friend and tutor Manas, and it's going to be yet another session in this lecture series on engineering mechanics. Well, today we're going to be continuing our discussion on the applications of work energy principle, and in that regard, here it is, and that's problem number 3 that we're going to be taking up today. Okay, first of all, I would suggest all of you to pause the video right now. Go and hit that pause button and go through this description. Okay, because that is going to be very beneficial. All right, now I'm assuming that you've gone through this description and you guys must have run your mind into this. Okay, now let me explain you what this setup is all about. So here we go. There is a package, okay, of 60 kg mass. So first of all, let me write all the given datas. Given. So there is this package having a mass of 60 kgs. All right. What else? A spring is used to stop a 60 kg package. So this is that spring and cable arrangement. Okay, and this package is sliding on a horizontal plane, right? With a velocity of how much? 2.5 meters per second. So let me write velocity of the package is how much? 2.5 meters per second. Anything else? Now this entire arrangement, or the springing arrangement, is having a spring constant of how much? 20 kilonewton per meter. So let me write this. Spring constant is represented by K, and that is equal to 20 kilonewtons per meter, which essentially means for a deformation of 1 meter, you need to apply a force of 20 kilonewtons. That's the spring constant. Okay, and you know very well that the spring force can be calculated very easily. It can be formulated as spring force F is equal to spring constant K multiplied by the deformation. It could either be compression, it could either be extension, whatever. Now, let me tell you something about this entire arrangement. Now, this is the relaxed length of the spring. Okay, so what they've initially done is they've initially compressed the spring by 120 millimeters. So let me write this. Initial compression of spring is how much? 120 millimeters. Guys, it will be better if we can convert this millimeters into meters. So this is going to work out as 0.12 meters. So you have this normal length of the spring, relaxed length of the spring. Then what you do? You compress it by an amount of 120 millimeters. Okay, 60 here and 60 here. So in totality, this is 120 millimeters compression, right? Then what you do is, with that much length of the spring, you fit it over here. Okay, and you set it up into that position with the help of this cable and this wooden plank, you can see. So this spring is already compressed, right? So there is already a retaliating force in the opposite direction. Okay, a spring force, you can say, which you can calculate by F is equal to Kx. That can be done very easily. So this spring is already in compression. Remember this. This is not the relaxed length of the spring. This spring is already in compression. Okay, now this is known to us. Alright, what happens is this package is actually approaching with a velocity v is equal to 2.5 meters per second. Guys, just try to think what will happen when this package strikes this entire arrangement of spring and cables and this wooden plank. What will happen? Well, obviously there is going to be some more compression. So that is the additional compression onto the spring. Okay, let me write this. Additional compression of spring. And that essentially has been given to us as, let me check, 40 millimeters. So 40 millimeters in meters can be written as 0.04 meters. That's it. Into 10 raised to minus 3 meters. Milli is 10 raised to minus 3. Remember that. Okay, so that was the setup all about. Now there are essentially two cases. Case 1, okay, or case A and case B. So I'm going to be implementing case A over here, where I'm supposed to find the coefficient of kinetic friction between the package and the surface. Now guys, this package is directly in contact with the ground over here, or the surface over here. So the surface offers some sort of friction, okay, and the coefficient of kinetic friction is something that we need to work out. So in case A, we need to find this coefficient of kinetic friction, and there is this case B, where we have to find the velocity of the package as it passes again through the position shown. Now, this is very interesting, guys. Let me explain you both the cases once again. So this package is approaching this spring arrangement. Okay, it's going to strike the arrangement and it is going to further compress it by an amount of 40 millimeters. So this is going to be position 1. Okay, and that's position 2. On the way forward, say from left to right. Okay, in that process it is going to compress the spring by an amount of 40 millimeters. Done. Okay, then the spring, what happens is the packet is traveling, it is striking the springing arrangement. What will happen is it is going to bounce back, the packet will again move back in this direction. Okay, and then it is again going to return to its initial position. This was its initial position. So again we are going to start from position 2 and we are going to return to this position, that is position 3. So here in position 1 we already know what the velocity is. It is equal to 2.5 meters per second. But guys, you should have been able to frame an intuition as to how much the velocity at 3 is going to be. Well, velocity as 3 is obviously going to be less than 2.5 meters per second. Okay, because of obviously friction. Alright, so that was all about the setup as far as this particular problem is concerned. So guys, now let's discuss case 1. And in case 1, what we need to do is we need to find the coefficient of kinetic friction. Okay, for that, let me zoom into this. And let us first of all work out all the forces which are acting onto this block. Well, firstly, let's say this is the center of gravity. Okay, so this block is having a mass of 60 kg if I'm not wrong. Yeah, so the weight is obviously going to act in the downward direction this way, and this can be written as 60 g. You just multiply 60 with 9.81 and this is going to work out as, let me see how much it is, 588.6 588.6 newtons. Now since this block is in contact with the ground, or with the bottom surface, there is obviously going to be some sort of normal reaction, some sort of reaction offered by the ground and onto the block. Let's say this is represented by N simply. So essentially, if you watch carefully, this N will be equal to this 588.6. That's true. Okay, now let's move forward. This block is moving along this direction, okay, with the velocity. We know very well that velocity is actually 2.5 meters per second. So obviously there is going to be some sort of friction, okay, offered from this surface onto this block, but in the opposite direction of motion. Let's say that this is the direction of friction force. Let me fix this. All right, now you know very well that friction force is represented by small f, and small f is actually a product of, since this is a case of motion, it's a product of kinetic friction, or the coefficient of kinetic friction, and the normal. And when you put in the values, you're going to get this mu k. We don't know what mu k is. We have to calculate the value of mu k. We know what N is. N is how much? It's 588.6. So we are going to write over here 588.6 times of mu k. Okay, so here let me write 588.6 times of mu k. So that's the amount of friction offered by the ground or the surface onto this package. Here we go. Now then, just think the total amount of distance traveled by this package. Well, the package first of all travels a distance of 600 millimeters, and then after it has traveled a distance of 600 millimeters, it comes into contact with the springing arrangement. Okay, then obviously the springing arrangement gets further compressed by an amount of 40 millimeters. So in totality, the distance traveled by the package in the right hand side direction is 600. This 600 plus 40, that is 640 millimeters. So this particular frictional force will be active for the entire span of 640 millimeters. That's for sure. Secondly, there is one more force which is going to act. But that force is going to act from here and it is going to end somewhere here. Okay, at this moment the spring comes into contact with the springing arrangement. All right, and then further compresses the spring by an amount of 40 millimeters, and for that particular time period there will be some sort of spring force. Okay, now let me explain you this. Let me zoom out slightly. Okay, let me have a coordinate axis. Where can I have a coordinate axis? Yeah, that's it. it's pretty good. Okay, let me use a black color. All right, so this essentially is a force, what I call a force deflection plot. Now, as I've already told you, the spring, whatever the spring's initial state was, whatever the normal length of the spring was, it initially was compressed. Okay, by an amount of how much? 120 millimeters. So corresponding to that 120 millimeters, there must have been an initial spring force. Now let's represent that by this. Let's say that initial spring force is represented by F minimum. We are going to calculate its value. Okay, watch this carefully. In this axis, y axis, we are going to have the force, and along this axis we are going to have the deformation. Okay, and as far as this particular case is concerned, it is compression, to be very specific. And here we're going to write everything in millimeters, mm's. Okay, let me shift slightly towards the right, and that's good. Done. So in order to calculate the value of F minimum, you have this. F minimum is equal to K, that is the spring force, or the not spring force but the spring constant, multiplied by deformation and the initial compression. So K is how much? It's 20 kilonewton meter. So essentially it is 20,000 newton per meter, you can say, multiplied by the initial compression of the spring. Well guys, initial compression of the spring has to be taken as 120 millimeters. So 120 millimeters essentially can be written as 0.12 meters. So you can clearly see meter and meter will cancel out. What remains is this. Okay, so if we just do this calculation, F minimum works out, it works out as how much? Let me see. This, where has it gone? 2400 newtons. So F minimum's value is 2400 newton. That's it. The next thing that we're going to do is we have to calculate the value of another spring force, okay, when there was a compression of 40 millimeters. So how can that be worked out? Let us see. So F minimum's value is how much? 2400 newtons. Let me write it over here. Okay, let's go ahead. We need some more space. Okay, so there was an additional compression of how much? 40 millimeters. So due to which there is going to be an additional amount of spring force. Let's say this is that compression, 40. Okay, and this is in millimeters, and for that we are obviously going to get, okay, a larger value of the spring force. Let's say this is that value, and this corresponds to F maximum. All right, so there is essentially a linear plot, you can say this way. Okay, a linear plot. Now what, you have to calculate the value of F max, and F max, if you watch carefully, I need to make some space. F max can essentially be written as F max is equal to this much, that is F minimum plus this much force. Okay, so F max is equal to F minimum, I need some more space, this way, plus K times of X. What is X? X is nothing but the additional compression, that is 40 millimeters or 0.04 meters, you can say. So F minimum has already been worked out, and this is 2400 newtons. So let me write it over here, 2400 plus K times K. K is how much? It is 20,000 newton per meter, and X additional is nothing but 0.04 meters. 0.04 meters. Well, obviously these two fellows are going to cancel out, and what remains is the final value of F max. Let me see how much it is. F max is equal to, let me see, this has been worked out as 3200 newtons. Now let me go ahead and highlight these two boys. That is F max, which is extremely important for us, and that's F minimum. Now let me go ahead and write that in the plot also. This has worked out as 3200 newtons. That's it. Now what? Now what? Okay, let me tell you something. We are going to directly calculate the work done by the spring force. Okay, and that can be done very easily. Let me show you something. If you have seen my previous lecture, where it is this one, yeah, in this lecture of work done by the force of spring, this is something that I had told you. Work done by the force of spring, negative of average force multiplied by the displacement. This is exactly how you can actually directly calculate the value of the work done by the spring forces. So I'll tell you two methods. This is the first method that I'm telling you right now. Okay, so this is gonna be very easy. Let me zoom out. We already have done a lot of things. Work done by spring force is equal to negative of what? Average force multiplied by deformation, and we know what the deformation is. It is equal to 40 millimeters. That's it. So negative of the average force. Okay, let's do this. Negative of average force. So one is over here, that is 2400, while the other one is over here. Let us zoom in. 2400 plus 3200 divided by 2. 2400 plus 3200 over 2. Let me put this into a bracket, and there was a negative sign also, multiplied by the deflection. Deflection is how much? It's 40 millimeters. So in meters, this is going to be 0.04. Just do this calculation. Let me make use of this calculator. So 2400 plus 3200 equal to 5600 divided by 2 is this much, 2800, multiplied by 0.04, and that's 112. Unit is what? It's joules, since this is work done. That's it. So work done by the spring force is essentially working out as 112 joules, but with a negative sign. So let me go ahead and highlight this also. All the important data have been highlighted. Okay, as I promised, there is one more way of working out the work done. Okay, let me go ahead and tell you how that can be seen. So let me zoom into this. So work done essentially, work done, okay, by the spring force is also equal to the area under the curve. And let me tell you exactly how this can be worked out. Okay, let me divide this into two parts. Now if you watch carefully, if you watch this rectangle over here, this rectangle, right, this rectangle is having a height of how much? 2400. 2400 multiplied by, okay, we want to find the area of this rectangle. So that's 2400, this vertical height, and this is how much? 40. And in meters, this is going to be how much? 0.04. And if you just do this calculation, 2400 multiplied by 0.04, this is working out as 96. Okay, so that is essentially 96 joules. And if I were to calculate the area of this triangle over here, it would be something like this: half of base is how much? That's the base, and it's 0.04 multiplied by this height. This is the height. And if I were to calculate this height, it would be, this is from here to here, that's 3200, and from here to here, that's 2400. So 3200 minus 2400, 3200 minus 2400. Just do this calculation. Let me do this into a calculator. 3200 minus 2400, this is 800, multiplied by 0.04, this is 32, multiplied by 1 by 2, or you can say multiplied by 0.5, and this is working out as 16. Okay, and on summing these two things, 96 plus 16 is how much? Plus 96, 112 again. So that's one more way of calculating the work done by the spring force is equal to 16 plus 96, and that's eventually 112 joules. But again, this is the negative work. You have to remember that. Always remember, work done by the spring force will always be accompanied with a negative sign. So why wait? Let me go ahead and let me give this some respect. This way. Beautiful. Beautiful. All right. Now let's get down to business. So essentially everything has been worked out. We just need to apply the work energy principle. And since over here in position 1, this is the position 1 and this is the position 2, and in position 2 the package is virtually at the in the position of rest, that is v2 is equal to 0, and if v2 is equal to 0 then t2 is also going to be equal to 0. So if an object does not have any velocity, its kinetic energy is obviously going to be 0. Okay, and here we can actually calculate the amount of kinetic energy. Let me tell you how. Now in this position the block is having a velocity of how much? 2.5 meters per second. Let me choose slightly. So T1 is going to be equal to half of mv square. Half of m, mass of the package is how much? 60 uh, 60 multiplied by velocity is how much? 2.5 meters per second. So 2.5 square. Just do this calculation. T1 eventually will work out as 60 dot into 2.5 square whole divided by 2. This is working out as 375 by 2, 187.5. Well, 187.5. That's the initial kinetic energy with which the block was in position number 1. And let me go ahead and highlight this also. Done. Now we'll straight away apply the work energy principle. Let's kick off. We are ready to go, man. Let me apply that principle over here. We have lots and lots of space over to the right. Okay. So work energy principle for position or between position 1 and 2 is obviously going to be equal to the change in kinetic energy, that is kinetic energy at position 2 minus kinetic energy in position 1. Okay. So between position 1 and 2, the total distance traveled is how much? 600 plus 40, that is 640. And during this span, the force which has worked out thoroughly, is nothing but this friction force. So 588.6 mu k, okay, 588.6 mu k is the frictional force, right? And this has been acting for a distance of how much? 640 millimeters, that is 0.64. But watch carefully, guys. The block is moving this way. Okay, so the motion is happening over here, but the friction force is acting in this direction. This is the direction of motion, this is the direction of frictional force, opposite directions, negative work. So this essentially has to be accompanied with a negative sign. Let me put that negative sign over here. I don't know whether that's visible or not. Let me zoom into this. Can we zoom it further? There is a negative sign. That's it. Okay, fine. Secondly, we already have worked out the work done by the spring force. How much is that? Minus of 112 joules. So you can directly put that value, minus of 112, which is essentially equal to the kinetic energy at 2, that's 0, minus kinetic energy at 1, that's 187.5. 187.5. Now this is one single equation and there is only one unknown, and that's this fellow, mu k. Okay, that's pretty simple. So let me do this calculation. This is going to be very easy. This is minus 376.7 mu k minus 376.7 mu k minus 112. Okay, is equal to minus 187.5. Minus 187.5. You just have to solve this, and the final value of mu k obtained, the coefficient of friction, is going to work out as 0.20. That's it. That's the final value. Let me use a different color for highlighting, pink one. So that was case 1, okay, where we were supposed to find out the coefficient of kinetic friction. Alright, now let's talk about case B. And in case B, what we need to do is we need to find the velocity. Okay, what is that velocity? First of all, let me tell you this. So we started with this packet of 60 kgs. It was initially traveling with a velocity of 2.5 meters per second, if I'm not wrong. Yeah, and there was a springing arrangement over here. So position 1, it moved, okay, and then it struck the springing arrangement, and it further compressed it by an amount of 40 millimeters. Total distance traveled was 640 millimeters. Okay, position 1, and that's position 2. Now, after compressing the spring thoroughly, the spring will retaliate by applying a force of, say, spring force. And because of that, the block will now move along this direction back to its initial position. And here, after traveling a distance of 640 millimeters, you need to find what the velocity right now is. So from 1 to 2 and from 2 to 3. And 2 to 3, in this time span, we'll be applying the work energy principle. So let's kick off. Here we go. Where is the diagram? Here it is. Okay. Now, since the motion is happening along this direction, this is where the motion is happening. Okay. Motion. So the frictional force will be acting in the opposite direction of motion. And friction force, guys, worked out as, where is it? Yeah, this was the friction force, 588.6 mu k. That same friction force will be over here also, 588.6 mu k, but the direction is obviously opposite. Okay, anything else? Well, we can directly apply the work energy principle now. Here we go. Work done in carrying the particle, not particle, but package from position 2 to position 3 is equal to kinetic energy at 3 minus kinetic energy at 2. And here you can clearly see, okay, at this moment, the velocity is 0. So the kinetic energy at 2 will be 0, and kinetic energy at 3 will actually be equal to half of 60 into V3 square. That's it. Okay. And if you can simplify this, 2 times of 30 is 60. You can also write this as 30 times of V3 square. So let's do this. So this 518.6 mu k, that is the frictional force, will be acting for a span of how much? 640 millimeters. So the direction of friction force is this way. Okay. The direction of motion is this way. That means opposite directions. Therefore, negative work. Where can I write this? Negative of, let me write this over here, 588.6 times of mu k, that's the frictional force, multiplied by the distance that it will be active upon, and it's 640 millimeters, that is 0.64. Okay, now there is something else which I need to tell you. In this position, the springing arrangement will retaliate, okay, and this entire arrangement will apply a spring force, F spring force. That force is towards the left hand side direction, okay, and this is the direction where the displacement is happening or where the motion is happening. So spring force is acting along this direction, displacement is acting also along this direction. That means positive work done by the spring force. Okay, so here, just opposite to the previous case, you have to put a plus sign. Okay, and you know very well the work done by the spring force is how much? It's 112 joules. Okay, let me show you something else also. Watch this. Here the motion was happening along this direction. This is the direction of motion. Okay, so there the spring force, okay, the spring was retaliating by applying a force in this direction, and here you can clearly see this was the spring force's direction. This is the direction of motion, this is the direction of spring force, opposite to each other, that means negative work. And here both of them are in the same direction, that means positive work. That's it. And which essentially is equal to kinetic energy at 3. And where is the kinetic energy at 3? That's 30 v3 square, 30 v3 square minus t2 is obviously 0. So guys, you just need to put in the value, and the value of mu k you know very well is 0.2. We have already calculated that, where it is here. That's it. And just put in this value, okay, and then solve for v3. Final value of v3 is going to be equal to, let me see, that's 1.105 meters per second. Okay, and let me go ahead and highlight this. Where is the highlighter gone? Yeah, the pink color. Beautiful. Okay, so here is the story, entire story. Okay, so there was a block or a package traveling at a velocity of 2.5 meters per second, headed towards a springing arrangement. It struck that spring, okay, then compressed that spring further by an amount of 40 millimeters. Then it was on its way back, and as soon as it reached its initial position, it now has a velocity of how much? 1.105 meters per second. And in that entire process, the coefficient of friction that we calculated was equal to 0.2. That's it. Well, so guys, that was all from my side for today. If you've got any doubt or query, do write them down in the comment section below. I'll be very happy to answer them. And if you believe that this video tutorial has added value to your knowledge of engineering mechanics, then do share and like this video, subscribe to this channel, and also press the bell icon, so that whenever I upload a new video, you get a notification, you get an update. Well, needless to say, I'm going to be back with more such videos on drawing and mechanics. Until then, it's a wrap. This is Manas Patnaik signing off. Take care, have a great day, and keep learning. Thank you.